Okay, great. We are on worksheet 5 already. Hope this is doing a good job of keeping you up to date on everything. I hope the worksheets and the quiz is all working out for you. If there's any issues, please let me know. We'll work on that. Okay. Okay, so you may think that the quadratic formula is obvious, but if you think that, then you don't realize that in different countries, the quadratic formula is actually done slightly differently. So if you haven't seen this before, it's okay, and if you think this is boring, that's okay too. So a parabola looks like this. You have 3 degrees of freedom. You have A, B, and C. It's the next polynomial up from the line. And if we want to find the roots, we're going to set it equal to 0 and solve for x. Okay? So the way this happens is there's a whole bunch of algebra. You do completing the square, whether you do it the European way or the American way. It doesn't matter. You got to complete the square. The difference is the Europeans do this divide by a all over the place, which makes a lot of sense. But sorry, the Americans don't do it that way. So we end up with x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. My sister-in-law taught me the song that I think has gone in and out of style, but I will sing it to you. X equals negative b plus and minus the square root of b squared minus 4ac all over 2a. Okay, don't say I didn't sing it for you. And there you go. What you need to remember is this piece here is called the discriminant. Okay, and if the discriminant is positive, 0, or negative, you get 3 different cases. If the discriminant is 0, you have one double real root. If the discriminant is positive, you have 2 real roots. And if the discriminant is negative, you get complex conjugate pair of roots. Now that's all assuming A, B, and C are real. This guy is real, this guy is real, this guy is real. If you want complex coefficients, then well, let's not go there. But that's we're assuming everything is real. Okay, and so you will have various problems to do in the homework that should be review. This should be enough to get you through those exercises. Okay, the next concept, I have an entire separate video, so I'm going to just do this quick plots super quick. And those of you who haven't seen this kind of thing before should watch the optional video on quick plots. Okay, so if I have a function that looks sort of like this, y equals, I'm going to make something up, 4, I don't care about the coefficient, I just care if it's positive or negative, x minus 3, x plus 2, and maybe x squared. The way I draw this for myself is I put a little dot with a circle around it to tell me that there's a double root at 0 based on this term. Based on this term, I have a root at x equals negative 2, so I put a little dot at negative 2. And then there's a root at 3, 1, 2, 3, and I make a little dot there. And that's my total of 4 roots. I have a 4th degree polynomial, and because this is positive, I know that my end behavior is going to be going off to infinity. I always start on the right. Don't start over here or over here, because you have to decide whether or not you've got an even or odd function, and what a pain. So just start either in quadrant 1 if your leading coefficient is, if you have a positive down here, quadrant 2 if you have a negative. Okay, so just do that and then trace back and get this shape going. There you go. So that's how you do a quick plot. If you see a double root, you hit the axis and come back. If it's a single root, you cut through like a line. Okay, so for more examples, see the other video. One thing I will do though is show you how to check this on Wolfram. Okay, so I'm just going to open Wolfram or Desmos, or if there's something else you prefer better, that's fine. You don't actually have to put the times signs in, but sometimes I like to. There we go, and we'll see how well we did. It's always a little nerve-wracking because maybe I messed up. Okay, so one thing that I did that was not right is I made the thing look more symmetric than it was, but that's fine. For the purposes of what we're going to do in calculus class, this is not a problem. If you are asked to plot this function, there will be more steps in the process and you will get more clues, and this plot will become, by the end of the course, you'll be able to plot it a lot more accurately by hand, and then your check on Wolfram will end up being more reassuring. But that is totally close enough for what we're trying to do with a quick plot. Just so that you will understand the quiz question, some definitions. If you have real roots, let me draw this complex plane for you. This is the complex plane. Here's the real axis and the imaginary axis. So if you have the number I, not the letter I, the number I goes there. The number negative I goes here. There's a 1 and there's a negative 1. Okay, so anything that is strictly on the real axis here is going to be real. Okay, and everything that's on the imaginary axis, strictly on the imaginary axis, is going to be imaginary. Everything else is complex. The rest of the world is complex. This is complex. So complex conjugate pair of roots would be like that. They're always top and bottom of the symmetric about the real axis. Okay, so you need to know that. If it's pure imaginary, it's going to be on that red axis, and if it's pure real, it's on the blue axis. Everything else is just complex. The imaginary and the real axes are complex, but I just wanted you to know that terminology because you sometimes want to specify if something's purely imaginary or not. Okay, so it took me longer than it should have to realize this as I was learning mathematics, that if you have 2 points uniquely determine a line, but it only takes 3 points to uniquely determine a parabola. And if you have a cubic, you could have 4 points uniquely determine a cubic. Now the caveat is that you don't want the 3 points to be collinear. So for example, as long as these 3 points are not in a line together, then they should be sufficient to uniquely determine your parabola. And similarly, you don't want some linear dependence on these guys, or you're not going to get enough information to come up with a unique third degree polynomial, third degree, or is a cubic. Second degree is a parabola. I don't really like calling it a parabola because you can do a parabola like that, or like that, or like that, and they're still parabolas. So I don't like calling the second degree polynomial a parabola, but that's what we tend to call it because it is a parabola provided the line of symmetry is vertical. Okay, so that means you can solve these guys. That means you can think about this instead of geometrically, you can think about this algebraically. So for example, if I have a word problem like I'll have on the worksheet, and I know the answer is supposed to be a parabola, then all I need is 3 pieces of information, usually 3 points or 3 other clues, so I can find A, B, and C. All right, so for example, let's say somehow in the word problem somebody told me that at 3 the value is 7, and at 4 the value is 9, and at 5 the value is, I don't know, 10. I literally just made that up. This is probably going to be nasty to solve, and I may not even finish solving it, but the problems that you have for homework shouldn't be that nasty. Okay, so I'm just making this up. Okay, so let's try to do this. What you want to do is you want to just let each one of these guys I'm going to try to change color here. I'm going to put 3 and 7 in. The first point goes into y equals ax squared plus bx plus c. And I end up with the same situation down here for the next 2 points. So 9, 10, at some point this becomes really easy. 4 squared, 5 squared for 5. Okay, so what does this look like? 7 is equal to 9a plus 3b plus c. 9 equals 16a plus 4b plus c. 10 equals 25a plus 5b plus c. Okay? So you have 3 equations and 3 unknowns. And you have to just figure this out. So you can subtract things from each other. So I'm going to subtract these two, and I'm going to subtract these two and see what happens. I'll take the small one from the big one because it's easier. So I get 2 equals, what's 16 minus 9? I think it's going to be 7. 4 minus 3 is 1, and the c's drop out. 25 minus 16 should give me 9. Oh wait, I need the 1 first. 1 is equal to 9a plus b. Okay, in this case I got an interesting situation because I have b's in both places, so I can then subtract these guys again, and then I can say negative 1 equals 2a, and negative 1/2 must be a. I can feed that back in here and say 2 is equal to minus 7 over 2 plus b. 2 is of course 4 over 2, which means b must be 11 over 2. Let's see how horrible this becomes. And then let's chuck that all into the first equation here. 7 is equal to 9a plus 3 of the b's plus the c. Oh, it's the c we want. The a we already have. So multiply by negative 1/2, and again convert this into something more manageable. Plus 33 plus c, get rid of the 2's, and then you have 14 plus 9 minus 33 is equal to c. How annoying. I don't really want to do this, but I will. For you guys, I will. I don't really like arithmetic. It looks like negative 10 is c. And I want to see if I got that right because, you know, I do this wrong all the time. I'm going to double check. I'm going to see, how can I check that for you real quick? Well, suffice it to say, I found the error. You should have found my error. There should have been, when I crossed out the 2, I should have put a 2 here. There should have been a 2 here, a 2 here, a 2 here. And c is equal to negative 5. And now it's correct. And thank you, Wolfram Alpha, for finding my mistake. I will let you guys figure out for yourself how to coerce Wolfram Alpha into doing that problem for you. But there's many things we do in this class that you can double check on Wolfram Alpha, and that's fine by me if you do that. I do it all the time. But I want you to use Wolfram Alpha responsibly to check your work, not to avoid doing your work. Okay. On to the next topic. Okay, so here's the first example. Using tabulated values to determine what type of function some points came from. Here's the line example. You guys know this is a line, and by the way, all these examples, the ones that you're going to be doing in your worksheet, these guys have to be equally spaced. You can do this exercise without equally spacing them, but it makes it way harder, and we're not going to do that. So what do? You look at the changes, like you know this is a line, but you just sort of like go like this and say, okay, plus 1, plus 1, plus 1. If all the changes are the same, then you have a line. Of course I'm going to use the easy example for myself, but it's the same process that you have to use on the homework. So here's a second example. This is for exponential functions. So you remember the exponential functions had this kind of format to them. So what we're testing to see is if we have equal time steps from here to here, are we getting the same multiplicative ratio? So now when we look at the change, we're looking at the multiplicative change. 9 divided by 3 is 3. So instead of subtracting, we're dividing between elements to see if we get something that's constant. And so because these guys are constant, we say, yay, constant ratio differences. So this is an exponential. Okay, so let's say you want to test for a parabola. You already tested to see that it wasn't a line. You can tell by looking, that's not a line. And perhaps you can tell that that's not exponential either. And so you decide maybe it's a parabola. So you'd still go through the first step the same as if you're looking for a line. And then what you do is you see if the differences themselves form a line. These guys themselves, so the differences form a line. And so it's a parabola. And you may say, what? If this is the first time you've seen this trick, you're probably having your head explode right now. And that's totally okay. A lot of times in math class, we just casually say things to our students and we just watch to see if their brains explode. So it's one of these things, if you're not bothered by this, you're not paying attention. So hopefully you're paying attention and you're like, how come nobody ever told me this before? Or you've seen it before and you're like, yeah, I knew that. Okay, so what happened is I did a sneaky little trick. I just had you take your first 2 derivatives, but we'll talk about that later. But if you did take calculus before, you know that if you take 2 derivatives of a parabola, you get back to a constant. Okay, so we just essentially did this numerically. And you may ask, hold on a second. If you're thinking, you're like, wait a second, does the following work? Let's try this one more time, one more level deep. Let's do these differences. Okay, I just added 8. 9 plus, gosh, I can't even do this. I just created this puzzle and now I can't do it. I think I added 12. Now how much did I add? Did I just add 8? No, I just added like 17. Hold on a second. I don't even know if this example is going to work out. So let's just go ahead and try it. And I don't even know if I got the arithmetic right. If it fails, it fails. Who cares? Then I'll show you an example of something that's not working, which is what most of your homework's going to be anyway. 17 up to 20 gives you 3, so it's 6. Oh, this is working. Okay. All right. So we got this far until we got them to be equal. So this means if we got this column of differences is not equal, so it's not a line. So it's not a line. And this guy is a line, but they're not equal. So it's not a parabola. And so this one means it's a cubic. And if you notice, I was sneaky. I added in one more set of values, one more point, because if I simply gave you this much information, you could always create a parabola. The question is whether or not this point is part of the parabola created by the preceding 4 points, because 2 points determines a line, 3 points is going to give you your parabola, and 4 points is going to give you your cubic. So I couldn't very well give you 4 points and ask you if it could be a cubic, because by definition that's exactly how much information you need to create a cubic. So this is another piece of information that you need to know for your homework, your quiz, is that if you have exactly the right amount of information, you can automatically say, if there's 2 points, you can say it fits a line. If there's 3 points, you can say it fits a parabola. And furthermore, if you have 2 points, you could say it also fits a parabola, because the point is you could take those 2 points and add any other third point you want. So if you have just 2 values, then you can make a higher order polynomial. You just can't make a lower order polynomial. So line or higher, for example, 3 points gives you a parabola or higher. 4 points gives you a cubic or higher. Okay, intermediate value theorem. I like to call it the well-duh theorem. Well, what it's telling us is if you take any old f that's a smooth curve, and we'll talk about smoothness in a second. Okay, so this is a very precise definition, but it is exactly what you think it is. All right, and it goes from A to B, so x goes from A to B, and in the y-axis it goes from f of A to f of B. It could go downhill, uphill, whatever. Even f of A and f of B could be the same, it doesn't matter. But this is A, this is B, this is f of A over here, and then here's f of B over here. The intermediate value theorem says that for every k value that's between f of A and f of B, you can use equality or not, it doesn't really matter. It'd just be consistent. That you can find, so for any k value in here, you can backtrack and find at least one point on your curve that for which there's like a c value on the x in your independent axis, independent variable. There's c's that'll give you back those k's. That's all it's saying. It's saying if you went smoothly between a and b to get from f of A to f of B, all those points you pass through are somewhere. So you could think of this as being like a temperature graph. This is temperature versus time. Okay, this could be temperature over time, and you say like if at noon it's a certain temperature, it's 70 degrees at noon, and then at 4 p.m. it's 100 degrees. Well, then that means at some time it must have been 80 degrees. That's all it's saying. Like you can find the time at which it was 80 degrees. Or it's saying if you're measuring the height of somebody as they grow up and they're 3 feet tall at some point in their life and later they're 5 feet tall, you can say, I never saw them when they were 4 feet tall, but I know they were 4 feet tall at some point in time. That's all it's saying. It's like, well, duh. That's why it's the well, duh theorem. And you've probably seen this piecewise notation before. I just want to make sure you're aware of how it works. If we want to define a function that is defined differently over various pieces, so like I just made this function up. I don't like this function. I'm just making it up. I'm just going to say I have a function and I want to define it over 3 separate regions. I want the region where x is less than -10, where x is greater than 10, and then the between. So you just have to say, over here you say where, and then over here is like the different pieces you define. And sometimes people say if or when or for all, they put other symbols in there. The one thing you got to be careful of here is this, make sure that if you're using, you know, a certain kind of inequality in the first one, that it doesn't overlap this one. Okay, so if I'm going to use an if I choose to use an equal sign here, that's fine, but then I have to get rid of it over here. If I want to use an equal sign here, then I got to get rid of it over here. So just make sure you only define the function once at each value. You can be forgiven if what you're doing is you're creating a continuous function. And for example, I can say find k that makes this continuous. If I solve for k, then I'm totally fine to put that equal sign back in if it's in the context of having a continuous function. If that's a constraint on my problem, not just a subsection of an exercise, but the point is I'm dealing with some kind of physical continuity and I know it's continuous, then that's okay. But if there's any kind of discontinuity happening at -10, like it is here, then you absolutely have to make sure you only define the function once at each point. Okay, so we're going to start talking about limits, and so I'm going to give you just the basic definition of what it means to be a limit, because we'll continue to talk about limits through the semester. But if you have some kind of function, a typical continuous function, we're going to have, say there's a point here, f of A is how you label that point. In this case, since it's continuous, that as you approach this point from the left and as you approach this point from the right, then those limits are the same, then that limit exists, and if the point at the value of that function is the same, so limit from the left and limit from the right, if they're equal and it's equal to f of A, if those three things are true, then we say the function is continuous at a. It's probably actually easier to think of when you would have a discontinuity. And I like this example like Google Maps. Okay, Google Maps apparently has people driving off the edge of the cliff sometimes. Let's say you have a cliff, right? And you have a road or something. And down here you have something else going on with your function. One of these should be like an empty circle or something. So you're driving your car along like this. Give it an antenna and some windows. And it's okay if you're driving along from the left, but you have to stop here, because if you keep going, you're going to go off the edge of a cliff. That's a discontinuity. So the limit from the left is whatever this value is, let's say 10. But the limit from the right, this other car, I'm going to draw my car backwards. I don't like drawing backwards cars, but I have to for a limit from the right. That guy has a limit of 0. So the limit, so you would write limit of f of x as x approaches 0, and you use this little symbol to mean from the left. That's what that negative sign means. That's going to be 10 in this case. But what's the limit of f of x as x approaches 0? And we're going to use the positive. From the positive, I put it in the wrong place. The symbol has to go to the right. Sorry. Otherwise it just looks like a sign. So we put the sign on the opposite corner. It kind of looks like an exponent. Okay, and then this guy, limit from the right, is 0. These guys are unequal. So if we ask for the limit as x goes to 0 of f of x, we're going to say d n e. Capital D, capital N, capital E is an abbreviation, is a standard abbreviation that means doesn't exist. Does not exist. Okay? Yeah. In this case, f at this f of x, I'm going to just put the x here so you know which x I'm talking about. In this case, f of x equals 0, but it's irrelevant. The function's already discontinuous because there's a jump there, and we have a jump discontinuity. Okay. There's other types of discontinuities. We should be talking about that. You really can't talk about continuity and limits unless you talk about them together, I guess. So you can have an asymptote. In this case, I can draw, let's say this is 4. In this case, I would say I have an asymptote at x equals 4, or I could say the asymptote is x equals 4. That's fine. And that's a specific type of discontinuity. And so in this case, limit of f of x as x approaches 4 from the positive side is negative infinity, and the limit of f of x as x approaches 4 from the negative side, well, that guy is equal to positive infinity in this case. So that would be the kind of notation we are looking at. And I think that is more than enough to help you get through your homework exercises. So basically, when I write these videos, I want to make sure at the very least I get you through the worksheets and maybe a little bit more. Okay, you need to know about removable discontinuities. So here's a classic example. It's going to be just a line with a hole in it. But what's happening is if you can take and say factor the numerator, so this is the algebraic way to explain this thing, but I also want you to understand it geometrically. Then essentially you cancel these guys out in all cases except x equals -2. At x equals -2, it's 0 over 0. Otherwise, you just plot this x equals y equals x plus 2. And let's see, you have an empty hole there. And then you have just like a nice line here. the line y equals x plus 2, and you can use this special function notation to explain it. X plus 2, if x is not equal to -2, does not exist if x equals -2. So that's two ways of writing that same thing. Now, the reason why it's called a removable discontinuity is I always used to think, oh, because they removed a point. No, that's not right. What removable means, it means patchable. It means like there's a hole in your roof and you can put a patch in it, so you can remove the discontinuity. In other words, it's only a single point, we can patch it up. So if the limit of f of x, in this case, is a removable discontinuity, if x approaches -2 from the left is equal to the limit of f of x as x approaches -2 from the right, right? If that's true, and it is, then we have a limit of f of x as x goes to -2 exists. If this limit exists, then we can patch the hole. Now we keep saying limit from the left and limit from the right, and it's a little bit cheesy because you're like, well, there's only two directions, but that's not always true. So normally you have an infinite number of directions. So you think about if you're in 3 dimensions and you're walking up a hill, there's a whole bunch of different ways of getting to the top of the hill. All those paths have to work in order to have continuity. You can't just have a cliff off of one side. Okay, you have to have all different ways of approaching, all different possible angles leading to the top of that hill. Then the top of that hill is continuous. But because we're only looking at this very flat world, we're looking at just a two-dimensional world, that's why everything seems to be, it's from the right and it's from the left, but it's to build up the concept to understand that from all directions the limit is the same. Therefore, if the point isn't defined there, it's okay, we'll just patch it over. So it's a removable discontinuity because we can just kind of fudge that out and pretend like that hole isn't there. And in terms of calculus, it doesn't hurt anybody to just get rid of one little point out of a function like that. Okay, so that's why we would call that a removable discontinuity. Okay, so the formal definition for continuity is you're going to say limit as x approaches some value from the left should equal the value of the function there and should actually equal to the limit from the other side, limit from the right. So if all three of these things all exist and are equal, f of x is continuous at x equals c. Okay? That's what it is, and that's my story. I think you have enough information to get through the worksheet. And if you have trouble visualizing what something will look like, feel free to explore Wolfram Alpha or Desmos so you can get a picture of that plot in your head. It's totally fine. Okay, but you need to understand what's going on. So make sure you use these tools in a way that enhances your understanding and not in a way which in any way removes your understanding. That's the whole end game, is to increase your understanding. So if the tools increase your understanding, that's great. If the tools are a crutch that's preventing you from struggling with the material and thinking about it, then you're not using it appropriately. So just ask yourself honestly, when you're using these tools, is this increasing my understanding or is it circumventing the learning? And that will tell you whether or not you're using the tool appropriately. Okay, well, I will see you in class. Take care.